So what we've done is we started with a differential equation. We separated it and integrated to solve for the y, the antiderivative function, and we were able to solve for the plus c if we were given a specific point, in this case 2, 1, and solve for the plus c. Now there are a whole series of solutions with different plus c's though. Okay, and we graph those and we can see that that differential equation, the same differential equation, can have a whole series or family of solutions. So what can we do? Well, when we have a differential equation, we can get an idea what that family of solutions look like by generating something called a slope field. And a slope field is a field of slopes, essentially. And those little slope segments, so these are called slope fields here, these pictures. And these slope fields are generated by calculating the slopes of different line segments by plugging in x and y coordinates. So, for example, I've kind of drawn this here in red. If I want to find the slope at these different points, I plug in the coordinate into the derivative function to calculate the slope, and then I draw in a short line with that particular slope. So, for example, if I want to find the slope segment at 4, 0, I take the coordinate x is 4, y is 0. I plug it into my differential equation. It will tell me what the slope is. In this case, it looks like the slope is maybe, some steep slope there. And once I calculate it, I just draw it in. And every one of these lines has been calculated by plugging in the x and y wherever these slope segments are located. Okay, so wherever these slope segments are located, we just plug in x and y, calculate the slope, and then we draw in that particular slope for all these different x and y coordinates. And by doing that, we generate an entire field and of slope segments that look like this. And what this is useful for is this allows us to see what the general solution or the family solutions might look like for that particular differential equation. So this slope field, if we kind of draw in the different possibilities, which I've done in blue here, if we start at a specific x and y, that means I have an x and y coordinate that I can plug into my solution, which allows me to solve for the plus c, and it gives me a specific solution. So if I substitute x and y coordinates, it allows us to find a specific plus c for a specific solution through that slope field. And we can estimate that specific solution by taking a look at that, starting at that point. So in this case, we can start with a point that looks like about 3.5. And if I follow the slope field line, I can then trace out that one specific curve. Okay, but we're just estimating it by following the slope lines. Okay, and that's all we're doing is we're trying to get an idea what the specific solution through that point looks like by tracing it through that point and following the slope lines to guide us. So the specific solution is found starting at a known point, and then that's tracing out, following that known point and following the slope field to come up with a specific solution. And that is the same as algebraically finding that plus c by plugging in that point that we know the graph passes through. So there's two ways to do it. One way is algebraically, we solve for the plus c like this. So we anti-differentiate, we plug in x and y to find the plus c. An alternative is to generate a slope field, start at an x and y coordinate, and then we can trace out the solution based on the slope field. So this is particularly useful when we have a differential equation which is not solvable. So we are not able to anti-differentiate this, and then we're stuck. But if we know what the slope field looks like, we can then estimate what that function is going to be by tracing out a solution through the slope field.